When scientists talk about planets being more habitable than Earth, they are not saying these worlds would be comfortable vacation spots. They are using formal measurements like the Earth Similarity Index and the Habitable Exoplanet Catalog to rate how well a planet might support life based on size, temperature, orbital stability, and star type. By these metrics, Earth scores around 0.829 on some scales, while certain exoplanets score higher. The concept of superhabitability, introduced by astrobiologists Renee Heller and Rory Barnes, suggests that slightly larger planets orbiting long-lived K-type stars might offer more stable climates, shallower oceans with more coastline for biodiversity, and billions of extra years for evolution compared to Earth. K-type stars burn steadily for up to 30 billion years, far longer than our sun's 10 billion year lifespan. This extended time frame means life could have dramatically more time to evolve complexity. The catch is that most of these high-scoring worlds come with hidden problems. Many orbit red dwarf stars that bombard them with radiation. Others are tidally locked, meaning one side always faces the star while the other remains frozen. Some have crushing gravity or thick hydrogen atmospheres that would kill an unprotected human in seconds. So when we say a planet is more habitable than Earth, we mean it on paper, using models and projections. We do not mean humans could walk around on the surface breathing normally. These are theoretical havens for life in general, not necessarily for us. Kepler 442b sits about 1,200 light-years away, orbiting a quiet K-type star in the habitable zone. It is a super-Earth, roughly 1.3 times Earth's radius, and in a widely cited 2015 habitability index, it scored 0.836, while a hypothetical perfect Earth twin scored 0.829. This makes Kepler 442b one of the top candidates for being more habitable than our home planet. The star it orbits is cooler and more stable than the Sun, which means fewer destructive flares and a longer lifespan. Because it is probably not fully tidally locked, the planet might avoid having one hemisphere in eternal day and the other in permanent night. Instead, it could have a more Earth-like day-night cycle, which would allow for more even heat distribution and potentially more diverse climates. Scientists estimate it has a 97% chance of being in the habitable zone, higher than any other known exoplanet. What makes this eerie is how ordinary it appears from a distance. It ticks all the right boxes for liquid water, stable temperatures, and a long-term habitable environment. But we have no atmospheric data yet. We do not know if it has air, oceans, or a magnetic field to protect it from cosmic radiation. It could be a lush biosphere with complex ecosystems, or it could be a barren rock with gravity strong enough to crush human bones over time. Until we can study its atmosphere with future telescopes, Kepler 442b remains a perfect candidate on paper and a complete mystery in reality. Kepler 452b orbits a G, two-star almost identical to our Sun, about 1,400 light-years away. The planet is roughly 60% larger than Earth and completes one orbit in 385 days, just 5% farther from its star than Earth is from the Sun. NASA has described it as one of the closest analogs to the Earth-Sun system we have ever found. The orbital distance and insolation, the amount of solar energy it receives, place it well within the classical habitable zone where liquid water can exist. But the unsettling part is time. The Kepler 452 system is about 6 billion years old, roughly 1.5 billion years older than our solar system. That means Kepler 452b could have been sitting in the habitable zone for 6 billion years, longer than Earth has even existed. If life arose there on a similar timeline to Earth, it would have had an extra billion years to evolve. That is enough time for simple microbes to become intelligent civilizations, or for intelligent civilizations to rise and fall multiple times. Alternatively, it could mean the planet has already passed through climate tipping points and turned into a greenhouse nightmare, a warning of what Earth might become if our own climate destabilizes. The planet likely has stronger gravity due to its larger size, which might result in a thicker atmosphere better at retaining heat and protecting against radiation. But without direct observations, we cannot know whether Kepler 452b is a thriving world with advanced ecosystems or a dead planet that has already exhausted its habitability window. The Kepler 62 system, located about 990 light-years away, hosts at least two potentially habitable super-Earths orbiting a relatively quiet K-type star. Kepler 62f is only 40% larger than Earth and sits in the outer habitable zone. Climate models from UCLA show that with a thicker carbon dioxide-rich atmosphere, it can maintain liquid surface water even though it receives less sunlight than Earth. Simulations indicate the planet can stay temperate across a wide range of atmospheric conditions, up to roughly 12 times Earth's atmospheric pressure and up to 2,500 times our carbon dioxide levels. This makes it a strong candidate for being a deep global ocean world. If that is true, Kepler-62f might have no continents at all, just endless ocean under a dense sky. For humans, that scenario is both idyllic and terrifying. Any intelligent species that evolved there would develop without access to metals, fire, or easy paths to space. You cannot smelt iron underwater. You cannot burn wood for warmth or energy. Entire branches of technology that humans take for granted would be impossible. The star Kepler-62f orbits is about 7 billion years old, much older than the Sun, which gives life an extra 2.5 billion years to evolve compared to Earth. If life started there at the same time it did here, it could be far more advanced by now, though constrained by the lack of land and traditional resources. The oceans on such a world could be hundreds of kilometers deep, creating pressure environments and ecosystems entirely unlike anything we know. Teegarden's star is a red dwarf only about 12 light-years away, and it hosts at least two roughly Earth-mass planets, designated B and C, both in or near the habitable zone. According to the Planetary Habitability Laboratory, Teegarden B currently has the highest Earth similarity index ever calculated, thanks to its Earth-like insulation and minimum mass near 1 Earth mass. On paper, it looks like the closest thing to a twin of our planet that we have discovered. But the disturbing part comes from the host star's history. Red dwarfs spend their youth blasting nearby planets with intense flares and high-energy radiation that can strip away atmospheres over millions of years. Teegarden's star is now comparatively calm and about 8 billion years old, so any atmosphere on planet B or C has endured an extreme evolutionary gauntlet. Models suggest Teegarden B could be tidally locked, with one side permanently facing the star and the other side frozen in eternal darkness. If it has water, the planet might be temperate and habitable, with oceans on the day side and ice on the night side, and a narrow twilight zone between them where conditions are stable. Or it could be a bare, airless rock that was sterilized long ago during its star's violent youth. The proximity of this system, just 12 light-years away, makes it a prime target for future atmospheric studies. But until we can directly observe the planets, we cannot know whether Teegarden B is a habitable world that survived its star's tantrums, or a lifeless husk that serves as a warning about the dangers of living around red dwarfs. K218b is an 8.6 Earth-mass planet in the habitable zone of a cool star about 124 light-years away. It has become the prototype for Hycean worlds, a new class of potentially habitable planets with deep global oceans beneath hydrogen-rich atmospheres. Observations from the James Webb Space Telescope detected methane and carbon dioxide in its atmosphere, with abundances best explained by a water-rich interior and potentially large oceans underneath. Hycean planets are unsettling because if they are habitable at all, they may be better niches for life than Earth, yet utterly hostile to humans. Picture kilometers deep, high-pressure oceans, hot at depth, capped by thick hydrogen atmospheres that would be instantly lethal to anyone without a pressure suit and breathing apparatus. The hydrogen acts as a powerful greenhouse gas, which means Hycean worlds can stay warm enough for liquid water, even far outside classical habitable zones. This expands the potential number of habitable planets dramatically. There might be vast populations of hidden habitable worlds we cannot recognize yet, dark ocean globes wrapped in clouds, orbiting faint stars or drifting farther from their suns than anyone thought life could tolerate. Some may be tidally locked, with only a narrow crescent of ocean under permanent twilight truly hospitable to life. Later studies have cast doubt on whether K218b is truly a temperate water world or more of a mini Neptune with conditions too extreme for life. This illustrates how fragile the line between habitable and uninhabitable can be. A small change in atmospheric composition or internal structure can flip a planet from promising to impossible. On tidally locked exoplanets, the terminator zone is the band between permanent day and permanent night. Climate models show that under the right atmospheric thickness and composition, this twilight ring can maintain liquid water and stable temperatures, even when the rest of the planet is either searing hot or frozen solid. The substellar point, the spot where the star sits directly overhead, can become volcanically hot while the night side turns into a glacial wasteland. But the terminator zone, where the sun never rises or sets but hangs forever at the horizon, can remain temperate. This idea is both promising and deeply strange. Whole biospheres might exist as narrow planet-encircling strips where wind, clouds, and climate are locked into perpetual flow between fire and ice. Any intelligent species evolving there would live in a world where the sun never moves in the sky. They would see the same red or orange twilight their entire lives, with darkness on one side and blinding light on the other. The habitable ring would be a place of constant wind as air moves between the hot and cold hemispheres. A small orbital perturbation or atmospheric loss due to stellar flares could push the habitable ring to collapse inward or outward, wiping out the only livable zone. Life on such a world would be perpetually vulnerable to shifts that would be minor events on Earth but catastrophic there. The concept forces us to rethink what habitability means. It is not just about being in the right place, but about maintaining the right conditions in a narrow, fragile band that could vanish if anything goes wrong. Heller and Barnes have argued that Earth may not be optimally habitable. K-type stars, which are cooler than the Sun but hotter than red dwarfs, can burn steadily for up to 30 billion years. That offers a far longer window for complex life to evolve than the 10 billion years our Sun will last. Super-Earths in the habitable zones of K-type stars may retain atmospheres more easily due to stronger gravity, maintain vigorous plate tectonics for longer periods, and have broader areas of mild climate than Earth does. Kepler 442b, Kepler 62e and F, and planets around stars like Teegarden site close to this theoretical sweet spot. They orbit long-lived stars, sit in stable habitable zones, and have masses that could support strong magnetic fields to protect against radiation, and deep oceans to support diverse life. The implication is philosophical and slightly scary. If such planets are common, Earth may not be the template for life, but just one more middling world in a galaxy full of places that, statistically, should be better at nurturing biology than our home. We have always assumed Earth is special because it is the only place we know that harbors life. But if superhabitable worlds are scattered throughout the galaxy, we might be living on a planet that is merely adequate, not optimal. That raises the possibility that life elsewhere could be more common, more complex, and more advanced than we have imagined. It also means the search for life should focus not just on Earth-like planets around Sun-like stars, but on super-Earths around K-type and stable red dwarf stars, where the conditions for life might actually be better and longer lasting. Every planet on the list of more habitable than Earth candidates comes with conditions that would make human survival difficult or impossible without advanced technology. Kepler 442b might have gravity 1.5 to 2 times stronger than Earth's, meaning every step would feel like carrying extra weight, and long-term exposure could strain human hearts and bones. Kepler 452b, if it still has a thick atmosphere after 6 billion years, might have runaway greenhouse heating that turned it into a version of Venus. The Kepler 62 planets, if they are global ocean worlds, offer no solid ground to stand on, no way to mine metals, no forests for lumber or fuel. Teegarden B, if it survived its star's flare history, might be tidally locked with a habitable zone limited to a narrow ring. K218b, with its hydrogen-rich atmosphere and crushing ocean depths, would be instantly lethal to anyone without a sealed suit. Terminator Zone worlds would require humans to live in a permanent state of twilight with extreme winds and constant atmospheric circulation. Even if we developed the technology to reach these planets, adapting to them would require either genetic modification, permanent life support systems, or settlements deep underground or underwater. The term more habitable than Earth does not mean more habitable for us. It means these planets might support life, potentially complex life, more easily than Earth does. But that life would be adapted to conditions we would find alien and hostile. This is a critical distinction that often gets lost in popular coverage of exoplanets. The more we learn about potentially habitable exoplanets, the stranger the concept of habitability becomes. We have found planets that score higher than Earth on formal indices, yet almost all of them come with conditions that make them unsuitable for human life. We have identified worlds that might have had billions of extra years for life to evolve, yet we have no idea if life ever arose there or if it has already gone extinct. We have modeled ocean worlds, hydrogen sky worlds, and twilight ring worlds that could support thriving ecosystems entirely unlike anything on Earth, but we cannot yet confirm whether any of them are real or just theoretical possibilities. The paradox is this: the better a planet is at supporting life in general, the less likely it is to resemble Earth. And the less it resembles Earth, the harder it becomes for us to recognize or reach it. We are searching for life using Earth as a template, but the most habitable worlds in the galaxy might be so different from ours that we would not even recognize them as habitable without new models and new instruments. The planets discussed here represent the cutting edge of that search, but they also reveal how much we still do not know. Until we can study their atmospheres, measure their magnetic fields, and detect biosignatures, they remain Schrödinger's habitats, simultaneously promising and impossible, alive and dead, better than Earth and utterly alien. If you found this look at habitable exoplanets as fascinating as we did, consider subscribing. There is a universe of mysteries still waiting to be uncovered. And watch this video next. Thanks for watching.